Good morning, hello and welcome to the Royal Academy of Engineering's Education and Skills Policy Seminar Series. I'm Rhys Morgan, I'm the Director of Education and Engineering at the Academy and I'm your host for today. Last week we had a great COVID-19 skills discussion chaired by the Academy's Chief Exec, Hayat Salim. It was a wide-ranging discussion covering lots of aspects of education and skills and also issues around diversity. A great panel provided very thought-provoking content. So if you haven't seen it, do go and seek it out along with all our other webinars on the Academy's education pages of the website. Can I also take this opportunity to thank the team behind the scenes, Guy and Sophie, who do so much to get these webinars up and running each week. Thank you both. Okay, today we're talking physics. Now, my physics teacher said I had potential and then threw me off the bike shed roof. That's going to distract me. Okay, but what is going on with physics today in schools? We've had a new curriculum since 2014 that is packing more and more content in and lower down the key stages and age ranges, and many scientists and teachers are not very happy with it. We've had long-running issues with gender diversity. Only around 8,000 young women take A-level physics. That's about 3% of the entire female cohort, and that's been static for the last 10 to 15 years. We have teacher shortages in the subject that have been there for a very long time, and we just can't get enough teachers. Engineering departments are starting to offer places for engineering without A-level physics because they don't think the A-level curriculum is relevant for their courses. It's not looking great out there. So if you could design a physics curriculum that would engage and enthuse young people, help them to understand the world around them, and maybe just inspire a few more to go on to study further A-levels in the subject, what would it look like? That is the question that the Institute of Physics have been pondering for the last few years. And today we have my very good friend, Charles Tracy, the head of education at the Institute of Physics, to tell us where they've got to with their thinking. Charles is a former teacher himself, having taught in Hertfordshire for about 20 years, and a lovely part of the country it is too. He joined the Institute of Physics in 2006, and he has written various textbooks, been involved in curriculum development, and led subject-based teacher professional development sessions. He now runs the Institute's education programmatic and policy work, including some of the major programs, national programs like Stimulating Physics Network, the Improving Gender Balance, and the Teacher Training Scholarships. Among other things, he has spent the last 30 years worrying about the teaching of energy. I wish I had the energy to worry that long. Anyway, once again, a reminder that we will be doing a Q&A after Charles's talk, and the chat function is open. So if I can encourage you, if you've got any good physics jokes, pop them in the chat box. I do like a good physics joke, and maybe I'll read one or two out at the end. Okay, that's enough from me. Time to hand over to Charles to tell us about a new framework for the physics curriculum in schools. Charles.
Thank you, Rhys, and thank you to you and the Academy for setting up this sequence of webinars and inviting me to talk to you today. I've put a paragraph on this introductory slide that you can read while I'm chatting to give you something to reflect on, and I think it nicely captures a sense of the image and endeavour of physics that we would like young people to experience at school. It was written by John Ogborn as part of our process of thinking on the curriculum. And in some ways, our challenge has been to devise some guidance for a curriculum that reflects this cultured view of physics as compared with the one that Rhys described previously. So next slide, please. My aim in the talk, I'll top and tail it with some thoughts on the relationship between physics and engineering and routes through them. I'll suggest how we might structure the physics curriculum around three sets of big ideas, and most notably, and kind of the new bit, is the set of practices of physics, but also, of course, the substantive knowledge, which we have to include as well. That is the ideas and explanations of physics. Next slide, please. So in 2013, the Institute set up a curriculum committee, and it was chaired by Professor Mike Edmonds from Cardiff. And it was driven by a desire to improve the experience and utility of physics at school, specifically to have a curriculum that includes, as I mentioned, the practices and applications of physics, as well as that content. The committee comprised academics, physics and education academics. It had ITE tutors, teachers, recent students, and a mix of disciplines, including engineering and the other sciences. We produced some guidance, and we've run workshops with teachers to determine whether that guidance can be used to develop a curriculum framework. And I should say that all of this is still a work in progress, and we are working with the RSC and RSB to try and get a coordinated approach to the three sciences. So next slide, and then very quickly the one after. To start the top and tailing business, this is, I'm afraid it's a very complicated diagram, but we prefer not to think of the pathways through the system as a pipeline. Partly because that implies that there is only one destination, but also because the system is way more complicated than that, and we don't want to think of people falling out. They're still in the ecosystem. So this is perhaps a better way of imagining it, an ecosystem, and I do apologize for the complexity. If we focus on the academic route through physics, if you could click, Sophie, you can see that kind of the two main destinations are physics degree and an engineering degree. And sadly, if we click again, the one route that is absent is the route to technical pathways at level 4. More or less no one from physics A level goes on to anything other than a degree. Looking at it the other way around, if we think of the ways to get to engineering, so click again, it's multitudinous. There are many ways through the ecosystem at school to get onto an engineering degree. However, it is clear that a major route to engineering degrees is physics. A major job of physics at level 3 is to supply people, prepare people, and encourage them towards engineering degrees. Also, if we click again, I couldn't resist just putting a link in here, given that it is the ecosystem, that a good destination for engineering graduates is to go back into teaching. One way to ensure that engineering has a place in the school curriculum is to get engineers to teach physics. So that's a quick plug for our scholarships and the route into teaching. If we can go to the next slide. So how can we design a curriculum that achieves the aims above, that is for all students, for all pathways, and that includes people who don't go into physics and engineering at all, that gives them some backing, some underpinning for in a cultural sense. If we go on to the next slide. Our starting point in the curriculum committee was to provide some guidance for curriculum developers. And we wanted the guidance to be based on big ideas. And this was something that came up in the 2010 curriculum review, but was slightly lost in the detail as it developed into the GCSE specifications. But we were taken with it, the idea of big ideas, a set of big ideas. In a sense, they would identify what's truly important, maybe the sorts of things that people would still retain from their education 5 years after they've stopped studying physics, the sort of pub conversations you would have about physics. And they wouldn't be about the detail, they'd be the impression that physics left with them. And I think that's where the cultural aspect comes in, but also there is the disciplinary knowledge or the skills that they take away from their education that they may not realize came from physics, but their ability to problem solve or use numerical techniques would have been developed partly in the physics classroom. I think the other thing about a big idea is that it has depth beyond the statement. So we don't want statements that students rote learn, such as a statement of Newton's first law, good though it is. What we want is that they have a sense of what that means in terms of explaining and predicting behaviors of planets, bicycles, people on buses, and so on. So they will use the practices of physics and the develop the ideas and explanations of physics in a way that leads towards a set of big ideas, and those big ideas have rigors. They're not just statements that they rote learn. Some of the advantages of that are it gives continuity of content, that if you've got a sense of where you're heading with your ideas in physics, you can have continuity through the stages, and you have an end goal where you're trying to get to in your study of forces and dynamics. If we have the next slide. So when we're thinking of choosing content for a curriculum, I think what we're suggesting is that the main features of a curriculum based on big ideas are that the content should be chosen and described so as to provide a destination and purpose to the detailed content. That will help answer the perennial question from students of why do I need to study this? That if you've got a sense of the destination, both from the practices and from the substantive content, that question becomes easy to answer. The content should be long-lasting, should be chosen to be long-lasting. Big ideas are what students take away after they stop studying physics. There's the detailed knowledge underneath, but also all the transferable stuff that goes with it. I think it should obviously express an idea that is core to physics and valuable to the individual, and that's true for whether they continue with academic physics, follow a technical route, or pursue a completely unrelated route. We should try to illustrate the cultural value of physics through it, so to society at large. And of course, any physics should be inclusive, or more than that, it should not be exclusionary in any way. Next slide, please. So when we're thinking of structuring the discipline, we started with kind of 4 big questions. This is one way of thinking of the sciences. There are others, but these 4 questions are a good way that describe the endeavor of physics and the other sciences, and it will help us inform what should be in a curriculum. So what exists, why things happen, how do we know, and what can we do with that knowledge? And if we go to the next slide, you can see that for convenience, we've joined the first 2 together, which leaves us with kind of 3 questions, and we couldn't resist putting them on a cube because that has 3 dimensions. But it is a good way of showing also, or illustrating, I guess, that the questions are interlinked, that the different dimensions of a physics curriculum are interlinked, and also that they support each other, that the knowledge on its own doesn't really have any meaning without the understanding of the practices, how we can know that, and the epistemic question that's on the top. So it's worth noting, if you could click actually to answer these questions then. Yep. The physicists in the past have used a set of practices and ways of thinking, and they've used those ways of thinking, if we could click please, to develop the ideas and explanations that we know and love. Those ideas and explanations are based on a set of proposed entities and the way that those entities behave, so that you can see the questions about what exists and why things happen. Again, please. What we can do with it is apply those ideas, so solutions to practical problems outside the laboratory. Click again. Importantly, it works both ways. I think one of the risks we run with physics and engineering and applications is to think that all of engineering is derived from physics, but that is a highly simplified view. Much of physics is derived from engineering. We can think of thermodynamics, the physics of flight, information systems. All of those began in engineering and have led to new physics. And then finally, of course, we want them to, if you click again, if we want to have some practices that allow children to define and develop solutions to practical problems directly, so they get some experience of what it's like to think like an engineer as well. So if we move on to the next slide, that previous slide showed some sense of what physics is like. How does this then apply to the curriculum? So now we're thinking, if you click, I think the clicking's gone, yeah. And again, sorry. Now what we want is that students study a representative set of practices and ways of thinking and reasoning. So they're not going to be many physicists, but they should use some of the ways of thinking like a physicist. We're not expecting them to discover physics. What we're hoping is that their teachers model the ways of thinking that physicists use, and they themselves can model the way that physicists and engineers think. If you click again, I think that, yeah, so students employ and practice that representative set of practices, and click again, and through that they will they will do that as they study. So it's slightly different from physicists. Physicists use them to discover stuff, but students will employ them in the study of the ideas and explanations that already exist. And we click again. There will be illustrations from solutions to practical problems, and click again. Thanks. And that will they will also have experience of designing solutions to practical problems. So the kind of slightly disassembled cube for the curriculum represents, but it is not an exact copy of the cube for the study of physics. So what we hope is that students will get experiences and authentic experiences of physics and engineering through their studies. We can move to the next slide. Thank you. And therefore the kind of structure of the curriculum is it's three sets of big ideas that form this self-supporting cube, and we can think of them as being the practices, the content, the substantive knowledge, sorry, the practices of the disciplinary knowledge, the content, which is the substantive knowledge, and then applications. And we've been trying to call these the big ideas about physics, of physics, and from physics, but it's terribly difficult to remember which one's which, so I just stick with practices, content, and applications. Okay, if we can move on. So that's given us some sense of a way of structuring the curriculum. And it's worth noting here, in conversation with an education academic, he said 3 dimensions are too many. I said, what's the ideal? And the answer was 1. And of course, when you teach any curriculum, it is one dimensional. You're going from one point in time to another. But the point is to bring in some aspects of each of the dimensions, I think, some aspects of each of the dimensions in something you teach. So if you're teaching circuits, you will specifically talk about the practices and applications while you teach the content as well. So that brings us on to the practices. If we can have the next slide, please. So this is some attempt to try to get something from John's statement at the beginning. When we convened the curriculum committee, it was certainly the case that from the outset, the committee was more keen on the be able to do part of physics rather than should know part of physics. And we were calling it thinking like a physicist, and latterly kind of changed that into practices. And the reason was that partly the ways of thinking are what unite physics. Physics is not really the content, it is based on those ways of thinking, because physics in 100 years won't necessarily look like physics now in terms of the content, but the ways of thinking and the ways of arriving at the knowledge will be the same. So in some ways, physics is defined by those ways of thinking. But it's also that practices are useful in and of themselves. Learning about the practices helps answer in a gentle way the epistemic question. It should leave students with the confidence that they have confidence that the ideas of and explanations of physics are firmly founded because they've been well thought through and well tested. And as I say, the practices are useful in and of themselves, but of course they're not content free. So the content will be a part of this. I think it's probably also worth saying that this is knowledge, that the practice of physics is not skills, it is knowing how to think like a physicist, it is knowing how to do a practical, it is knowing how to solve a complicated numerical problem. So this is definitely knowledge, and hence we refer to it as disciplinary knowledge. If we can have the next slide. I think just to think about what the advantages of delineating the practices are, partly that it will develop capability in a well-regarded set of transferable skills. So if students are using the practices in their study and seeing teachers use the practices of physics in their study, for example, when they're learning about forces or electricity, be able to explain the phenomena, they will have learned some of those practices as well. And those making the details of these practices explicit, which is what we're coming on to, will also help people see the purpose of their studies, particularly those who aren't going on to study physics directly. So they may say, I'm never going to use electric circuits again. Why do I need to study electric circuits? And perhaps the answer is that learning about electric circuits helps you to think in a systems way. It helps you to understand, see in terms of little particles that you cannot see, and it is the continuous loop of those particles that allows a circuit to work. And all of those ways of thinking, the systems way of thinking and the explaining something in terms of something smaller way of thinking, will be useful to you in your later life. So the purpose of studying this is not so much to know that forever that current is proportional to voltage, be able to explain things and think better. The other reason that it was important to try and delineate these practices is to make explicit what is often implicit, either covered broadly by skills. Actually, I should say what is implicit in good teaching, but also is lacking in the broad reference to skills, which sometimes people say skills, but they're not quite sure what they mean by that when you challenge them. So we wanted to make it explicit. We wanted to know what the practices of physics are, what we thought the valuable ways of thinking are that physics provides for students. If we can go to the next slide. Other advantages of the advantages of the term practice. One is that it covers everything. So we looked at ways of thinking, we looked at practical skills, etc. But practices is a good term because it covers all of that. It describes both things that are beneficial, that in order to learn the practices, they have to practice them. They have to experience and take part and them to get better. And it does also sit comfortably with international systems. It's what's being used internationally now. So I have a very short section that normally would be interactive on the next slide. If we can have the next slide, thank you. That kind of illustrates this. I'll have to do it very quickly for you. So perhaps a thinking question here. A thinking question would be, here's a metal disc with a hole, a washer. What happens to the size of the hole when you raise the temperature of the disc, when you heat it? If this was an exercise, first of all, some people would say it gets smaller. In fact, it gets bigger. But the most important thing is to think of the ways that people think about that. So I would ask you to analyze how you got to the answer. And if we can have the next slide, typically the explanations of the hole getting bigger are based on a ring of atoms. So it's a model based on things you can't see. Or taking the thing to a limit. So if you were to think of a ring, like that ring, most people would agree that heating that would make the hole in the middle bigger. So that's taking the situation to a limit. And then you can apply it back to the disk. We could consider the bit that's taken out. So that's kind of a rational reasoning way of doing it. We could imagine a circle drawn on the disk and so on. So what's important from that, I'd say, is that all of the answers are consistent. Although there is a right answer, we could check that. We could do it empirically. And some of the ways of arriving at the answer relied on quite fundamental bits of physics. So to try to assemble these into thinking like a physicist, on the next slide, please. We've got the answers that physics is strictly consistent. It's no good in physics to have different ways of approaching a problem arrive at different answers. One of them would have to be re-examined. Physics often explains something we can see in terms of something we can't see. It often takes things to a limit. We use reason and logic. So generally that tells us that physics relies on models, it's empirical, and indeed we cannot rely on gut reaction. So often the gut reaction to that question is that the whole gets smaller, even when you know some physics. We then spent some time trying to organize these, and we looked at some other problems as well. And the table on the next slide, which we won't dwell on, but we had kind of some features of physics explanations that you seek deep understanding, you seek consistency, you use methods to test plausibility, etc., etc. And given that we are physicists, the committee was made up of largely people with a physics background. We wanted to bring some order to that. And the next slide is where we got to in doing that. So the colors relate to the previous one, that physicists tend to ask questions, look for explanations. They develop those explanations and refine them usually on a cycle of observing, reasoning, and thinking with models. So those are the next three things they do. They carry out experiments, they construct arguments based on thinking and reasoning, and they think and construct models. And often those models use numerical techniques or computational thinking. So to flesh those out a little, and I shall go over this quite quickly. On the next slide, we have those described in a way that might work in a school or a guidance for a curriculum. That those are the sorts of things through practice students should be able to do. And the detail of that covers what we might think of as the transferable knowledge from the practices, transferable disciplinary knowledge of physics. Okay, I mentioned that the practices are a part of it, but of course we've got to have, you can't teach them without content, and we do need students to learn some of the substantive knowledge as well. So on the next slide, which we can skip over, we will think about the substantive knowledge. And it would be quite easy but worrying if we ended up with a bullet list that looked like bullet lists that have been created in the past. In other words, a set of declarative statements that say that the resultant force of two forces can be shown by arrows on a diagram, and so on. So that's the typical structure of a specification, and I can see why they're expressed like that, but it feels regrettable that physics is reduced to a number of declarative knowledge-based statements like that. And we'd like it to be that we have some order to it, and we look for the patterns and the ways of thinking. So trying to bring some order to the substantive knowledge, what we have here is a wheel in 4 parts that looks a little bit like other wheels in multiple parts that have been used in these presentations. And if we click, we can say that generally physics explanations are based on constituents at the bottom, underpinning constituents of the universe, how those constituents behave, the patterns in that behavior, and how they are collected together into systems, and how we can analyze some behaviors in terms of systems. If we click again, I've put on kind of familiar domains of physics under each of these. So it's arranging the domains that are familiar in a way that will be slightly new perhaps. So the constituents, we start with particles, don't we? That we can explain much of the behavior of matter based on the fact that it's made of particles. And then those particles themselves have their own structure, atomic structure. Stars and planets are the other kind of big constituents we often study. We click again, the typical behaviors. We have interactions between objects that lead to forces and therefore motion. And we have wave behaviors. Clicking again. Typical systems that we study are circuits and electromagnetic circuits. And then finally, we have some patterns which are energy, equilibrium, and entropy. You can see that the 30 years that Reese mentioned has made it to the top of that pile. So the aim here is to provide something that's kind of familiar, but in a way that allows teachers and students to think of it, think of the linkages rather than disparate domains of knowledge within physics. So think of a smaller number of common themes. If we take this a bit further, and I won't dwell on this too much, but if we go to the next slide, we then will end up with a statement, but it is matter of made of particles which interact without volition. So that's quite a big idea, I would say, and it kind of fulfills the thing that 5 years later, as long as students remember, if they're going to remember anything about physics and the sciences, if they remember that the world and matter is made of particles, that's probably a success. But furthermore, that knowledge allows us to explain many of the observable properties of matter. So we've got a sort of so what statement as well. And what we've done with these then is to put together a statement that's a big memorable idea, and then what that allows us to think about, and they're grouped by an overall way of thinking. Now, it's true that there will be overlaps between these sort of headers, that in this case the constituents. So if we go to the next one, we've got the behaviors, and although we put these here, clearly the kinetic theory is partly about the constituents and partly about the behaviors, so there's overlap there. So there's those statements, and then I think if we just quickly move through the next two slides to show that we have thought about it, and the next one, because the other thing we want to show, and I noticed someone put an entropy joke in the chat, by the way, is disorder, which the ... is kind of to illustrate that this is still a work in progress. At the moment, there's not much on entropy and disorder in the curriculum, and I think some of us would like to see some more. So we're still thinking about that and how we might put it together. So we now have kind of two sets of big ideas. One is the ones relating to practices, the big ideas about physics, and a set of big ideas on the substantive knowledge, i.e. the big ideas of physics, or the content. And then if we move to the next slide, we're now just going to finish by thinking about the applications, the big ideas from physics, and how that feeds into engineering, and what the links are in a sense. So moving to the next slide, these are the statements as they now stand, and it is the case that engineering overlaps with physics here. So I mentioned at the start, I've got my notes in the wrong place now, sorry, just bring those down there. That physics has a role in preparing and encouraging future engineers as well as physicists. And I think that much of engineering obviously overlaps with or draws on the substantive knowledge of physics. So clearly, if we want level 4 engineers to have a good grasp of the ideas, explanations, theories, laws of physics, studying physics to age 18 is a good way of doing that. There's also overlaps with the disciplinary knowledge between physics and engineering, the mathematical models, the thinking and reasoning, and the ideas of systems. If we go to the next slide. So I put here, I hope it's okay, I've stolen Bill Lucas's slide on engineering habits of mind, and kind of put two wheels on a bicycle here, the engineering and physics bicycle, or the bicycle of physics and engineering. So there are overlaps in the disciplinary knowledge as well as the fact that both physics and engineering kind of operate in the physical world, and we're using things to explain and describe what happens in the physical world. There are disciplinary overlaps as well. The mathematical modeling, the thinking and reasoning, the ideas of systems, as I mentioned before. But it's also true to say that engineering has its own disciplinary knowledge. And this is a really important point. I think we often get slightly sidetracked or distracted, perhaps in arguments of which is best, more fundamental with maths as well. You hear people say that physics is just applied maths and engineering is just applied physics, and they will use the word just. And I think that's really regrettable. Any kind of subservient picture of the three disciplines, or a hierarchical structure of knowledge is not in any way helpful. I think they overlap. They overlap in the domains of activity, and they overlap to an extent in the disciplines. but they're unique and important disciplinary disciplines. So the engineering habits of mind kind of represent the disciplinary knowledge of engineering. And perhaps the most obvious distinction, I was talking to a friend of mine who is an engineering graduate and a physics teacher yesterday, and her view was that physicists tend to seek to explain and seek out more fundamental explanation. Engineers tend to use the explanations and ideas in order to design things that work and making them work better. So there's that's a broad difference and an important difference. And that's not to say either one is better, of course. However, it is the case that physics is the school subject. It's taught by people who've learned to teach physics, and the ideal is, I guess, to keep options open at school as long as possible. So by having students study a group of subjects at level 3 that keep their options open is a good thing. And it tends to be, to an extent, the same group of students who are contemplating physics, maths, or engineering at 16 and are yet to make up their mind. So giving them a route that lets them make that choice later is a good thing as well as providing them with the knowledge to go on to the next step. Therefore, it's the case that physics at level 3 must provide experiences of thinking like an engineer as well as thinking like a physicist, so that students can make informed choices, and that's an important part of any new curriculum, that there are opportunities to illustrate applications and both design and optimization thinking. But it is also the case that some of that will come from other subjects. I was looking at subject combinations yesterday. They're about, in England, because we get the data from England, about 29,000 students take A-level physics. About 85% of them, 25,000 students do physics and maths, that combination. Of that combination, 9,000 take chemistry as well. Very few, or fairly few, take DT with maths and physics, and that does seem a shame. That would be a fabulous combination for both physics and engineering at university. About 1,800 students take that. And quite an interesting combination, it seems to me, which is physics, computing, and design and technology, D&T, was 80 people in England chose that route. So our task is to produce some guidance for a curriculum. We haven't yet put that into a framework itself. That will be the next stage, and that may or may not be the Institute of Physics who does that, to develop actual curricula. That prepares students for life, for physics, and for engineering by thinking of the discipline as a combination of the disciplinary knowledge, the practices, the substantive knowledge, the content of physics, and the knowledge of applications and how to apply the knowledge. Thank you very much.
Wow. Thank you, Charles. Crumbs, lots to think about there. I've been scribbling down many notes, and I'm not quite sure where to start, other than to say typical for physicists to come up with a 3-dimensional model. Why not 6 or 12? You know, okay. So lots of things to think about, and the questions are starting to come in. And thank you also for the jokes, everybody. So I just let me pick up on a couple of things. So one of the questions around, you know, why is it, you know, why are we learning this? And, you know, there are many exciting things happening in physics right now, whether it's the quantum mechanics, the stuff going on in CERN, LIGO, you know, gravitational waves. I mean, these are quite difficult concepts, aren't they? And so I just wanted to test the kind of the question around conceptual understanding and whether children and at different ages have the cognitive ability to deal with some of these concepts. We do hear that, you know, children are taught at a young age about one explanation of physics in this way, and then they're taught later on the way we taught it before was wrong, actually it's this, and it gets more and more kind of refined or completely changed. And maybe that's not very helpful in and of itself. But just to get your thoughts on, you know, can we teach things like the Higgs boson to, you know, the things that are in the news? I remember your your predecessor at the institute said the only things you can teach children about Higgs boson is that it's called a boson, and it was thought of by a bloke called Higgs.
Possibly.
Your thoughts?
So first of all, that's all I know about it. So I'm not terribly well placed to talk about that. But I think you're right about making sure that we teach the right things at the right age, I suppose, is a way of thinking of it. That some ideas in physics are, you need a lot of backup, you need a lot of groundwork, and you probably need some, the ability to think in an abstract way and mathematical ability to analyze the situation numerically, and to interpret it numerically. And therefore, kind of trying to teach it too early is risky, that you run the risk of simply getting people to learn a fact, a bit of knowledge, that, let's say, electrons go around a circuit. But if you haven't begun to think in an abstract way, that doesn't really mean much. So we probably shouldn't mention electrons in circuits to 7 or 8 year olds. Far better, I would say, to actually, we've talked before, Reese, I think in primary school, it's phenomenological. It's about getting a feel for things happening, experiencing the physical world, and indeed manipulating it, because the way that you feel the material world, the physical world, is to manipulate it. And therefore, kind of DT is the foundation for physics in primary school.
So that's interesting. So, I mean, would you say that we shouldn't really be teaching physics in primary schools? I mean, is it just too complicated an idea for young children? Or is, as you say, kind of playing with magnets, just getting a feel for it? Is that kind of...
Yeah, so I think...
without trying to explain it, perhaps.
It is that. It's teaching them at an age appropriate moment the explanations, or going through the explanations with them at a time that's appropriate age-wise. I'd say the other thing about physics in primary school is there's nothing specific about physics that you need to know by the age of 11 in order to do next steps in anything, or to be a responsible and safe 11-year-old. And therefore, we should do some things in primary school, absolutely, but it doesn't particularly matter which things it is. So if a teacher prefers to build circuits and talk about components in a circuit, that's good. If a teacher prefers to make cars and talk about forces of motion, that's good as well. They're different experiences. It doesn't particularly matter, I don't think, which ones they have. It starts to get a bit more serious, what you have to do. It starts to get a bit more serious at Key Stage 3, because then you're preparing for exams at 16. But there's plenty of time in the 5 years of secondary school to make sure that.
Yeah. Just a key point, I suppose, is not to do linear circuits with the wires from a 3-pin plug. An important Key Stage 1 lesson.
Yeah.
Can I go on to? So I really like this kind of the practices, the content, the application. So this kind of, I love that you call it disciplinary knowledge instead of skill. It's a very clever move to get away from this the challenge around skills. But on that issue, the PISA 2015 results famously showed that international jurisdictions, countries that didn't do practical work, got better results in their tests. Can you just talk about that? Were they just testing the wrong things, or were they not seeing the whole picture of physics as you might want to see?
Yeah, so I mean, PISA are actually quite good at testing the right things. So I think it would be, I certainly would be careful about not being overly critical of that. So I should say also that practical work I would think of as having a number of purposes. One is, of course, to develop now the procedural knowledge, how to run a practical. The other is to get experience of things you should have experienced, to know what a Newton feels like, know what it feels like to raise the temperature of a liquid and so on. So get experiences of things you should have experienced. But another important part of it is simply to reinforce the nature of physics, that it is, and the sciences, that they are empirical, that the way that we develop knowledge is to do experiments and onwards. So I'd say also the disciplinary knowledge is more than just practical work. It's what you think about the practicals, or what you think about something you observe separately from a practical. So it is the thinking like a physicist, and using models, and using numerical mathematical formulations, relationships as well. Now, of course, if that starts to happen here, PISA may not have changed in time for that, and perhaps we shouldn't obsess too much about PISA. To an extent, I think the answer to your question, sorry, it's quite a long way around to it, is that whatever it was that PISA tested, if we were lacking, or our students weren't, or students who had not done practical work did better in that, although the aspects relating to practical work wasn't tested, that knowledge was still there. So it's kind of still worth doing, because it was a useful development of their knowledge during their education.
Yes, your colleague Mark Wally just posted a very interesting comment on the chat. Testing will never reflect anything other than the model of the subject it's designed to test.
Yeah.
Let's go to some of the questions from our viewers. Christopher Ingemels, I hope I've pronounced that correctly. Do you think that GCSEs are currently effective for checking the broad understanding of the big ideas?
No.
No. That's an easy answer. Would you care to elaborate? Is it because they have been kind of turned into these declarative statements that you talked about?
Exactly that, yeah. So it relates to Mark's point, and whilst I was careful to be polite about PISA, I think GCSEs test one particular type of knowledge. It is, if you look at a specification, it is a series of bullet points, more or less. If you look at a mark scheme, it is based on reproducing statements based on those bullet points. And it's very hard from a set of bullet points to get, or even answer those questions, to get any sense of kind of the totality or the story behind it. I think, I mean, one of the tricky things we have is that it is very conceptual. There's no question that physics is conceptual. And it's really hard to put in writing what your concept is. You mentioned my thinking about energy. I've written a few times on energy, but still people wouldn't really know what my conception of energy is. And I certainly don't know what theirs is, but I do know it's different from mine.
And it's wrong.
No, in that. But it's certainly impossible to capture that in a bullet point that says energy is conserved, or whatever it might be. Yeah. But then if an exam tests energy is conserved, you're not testing their conception of energy, and it would be really difficult to test their conception of energy. All you can test in the end in a written exam is performances based on the statements you put together. And if those statements in the first place were very declarative and very fact-based, that is what you will test.
So does the new model then, this kind of this four-spoked wheel, which I really like, does that require a fundamental shift in teaching?
I don't think it does, actually. I think it's a re-emphasis rather than a fundamental shift. So even when I talk to students or teachers about let's say forces, it's still forces as they recognize and know it. So I don't think we're proposing completely changing the way that the domains of physics are organized, and having it based on either applications or careers or cross-cutting themes. It will still be a topic on forces, but having in mind that the things that you'll learn through learning about forces go beyond simply knowing about Newton's first law and second law, and being able to use relationships like acceleration equals force over mass and make predictions. that it's the underpinning there as well, that when you do a homework on those relationships, you talk about the fact that you did a homework on those relationships. Isn't physics amazing that it allowed you to make these predictions? Isn't physics amazing that it allowed SpaceX to build a rocket that could go into space? Isn't physics amazing that it allows us to build irrigation systems in Africa and predict how much water we can pull up?
So the question then is Simon Lynn, I can't quite see your name, Simon, asks, is this a pedagogic challenge then? Is it just depends on the teaching practice? I mean, could we not take the curriculum that's there and apply your wheel to that?
More or less, I think. So, I mean, it's a very interesting thing about the physics curriculum. There'd be two ways of writing a physics curriculum. One would be to write at the top, teach them physics. And the other would be to write a load of statements. Now, at first thought, you may think those are very different, but actually they're more or less the same, because the set of statements is usually written for someone who has a background in physics, and they will teach it as they understand physics. So they still need to have the background in physics to teach it based on those statements. Anyway, yes, I think it is mainly a pedagogic issue. It's about emphasis and kind of making explicit, as I said before, making explicit things that are probably implicit in a lot of physics classrooms, but not necessarily all of them.
Okay, right. We are running out of time, and I want to get through some of these questions. So try and keep you waffled on too long, Charles, in your just like a physics teacher would. Okay.
Yeah.
Vicky Elston asks, given the underrepresentation of women in engineering, should we hold school-level physics teaching responsible for failing to appeal to women? Ouch. Or should we discourage people from thinking that physics is necessary or preferred for an engineering degree? And this is similar to Keith Jones's comment. Does an engineering degree need A-level physics as a precursor? You kind of touched on that in your presentation, but just a kind of your thoughts on that.
So I'm not sure if Keith made the link that you've made, that a reason for abandoning physics would be to increase gender diversity. I don't think it would, I'm afraid. I think that you would. It isn't the route through that is from there. I also don't think it's a question of physics teachers or physics teaching or even the curriculum. The work that we've been doing recently mainly shows that it's to do with whole school and societal attitudes. It's the way that that girls and young women are navigated in different directions through both unconscious and conscious steering. So they will be conditioned over their schooling and early life to be more compliant than their brothers. They will be conditioned to take fewer risks. They will be actually, in some cases, conditioned quite explicitly into thinking that they're no good at doing maths and that's not important for them. And it is those things that probably, we think, lead to the choices they make, or contribute to the choices they make. And I wouldn't say that if I didn't have it backed up by evidence. We've done some work in schools where we work with the whole school. So rather than with just physics teachers on what happens in the physics classroom, work with the whole school to make sure that there's nothing that puts different expectations on boys and girls, and particularly nothing that puts different expectations on boys and girls related to physics based on their gender. And when we did that, 6 pilot schools, we had a threefold increase in students choosing physics beyond 16. I think it went from 16 to 52 students, girls, and we're now doing a randomized controlled trial with 130 schools across England.
Great, thank you. I'm going to move on. AB says they have been teaching physics for 6 years, and there needs to be much more emphasis on energy. You're only 24 years behind Charles, AB. Asked a number of questions, actually. Could there be a national system for experienced physics teachers to have a reduced timetable to help with training other teachers around things, issues on energy, and so on. This challenge of energy is obviously a really difficult one. Should we be teaching it at all?
Can I pick up on there should be a scheme statement? There is. So the Stimulating Physics Network, we buy out. Yeah, we buy out experienced teachers for 1 day a week, and they work with teachers local to them. So if you look up Stimulating Physics Network on our website, you will find a school near you where there is a school-based physics coach who can provide, and they would be delighted to talk about energy. I've no doubt. What was you said, Reese, should we be teaching energy at all? Yes is the answer to that. But I think the care is that what we shouldn't do is to use energy as some kind of magic dust early on in physics and science education. Often what happens is it's used to explain things which it simply can't.
Yes, Philip Pullman, Northern Lights. We should just teach dust. That's the answer. Okay, one final question from AB. I have marked A-level and GCSE physics exams. The emphasis on things like the use of set squares is a bit bonkers. Can we do better? I can answer that for you, AB. Yes, you can do better. That's ridiculous. Okay, we're going to have to leave it there, Charles. Can I thank you once again for an excellent talk, really, really thought-provoking, and a great Q&A. We may ask you back again to talk about diversity if this experience hasn't been too painful enough. Can I also thank Vicky Elston, our new resident comedian, for all the physics jokes. You didn't tell my favourite, which is a photon goes to the airport and goes up to the check-in desk, and the clerk says, "Do you have any luggage?" And the photon says, "No, I'm travelling light." Okay, thank you also to Charles for lending me your electronic drum kit during lockdown. It's been a lot of fun. Maybe I'll give the viewers a demonstration at some point. That's it for us this week. Belated happy International Women in Engineering Day to all the amazing women engineers out there in the world. Next week, we're back to university with the legendary structural engineering academic, Professor Tim Eibel. Tim will be talking about the imperative that is climate change and how we need to change the whole focus on engineering in higher education to address that global challenge. It's going to be super interesting. Do join us at the same time, 11 o'clock next week. That's it for us. Good night, goodbye, whatever. Bye.